Hello everyone. In this video we'll go ahead and get started on chapter 2, where we will be looking at right triangle trigonometry and trigonometric functions of acute angles. In this particular video we'll be looking at right triangle trigonometry, the concept of cofunctions, and how function values change as an angle changes, and the quotient identities, and two special triangles, 45 45 90 triangles and 30 60 90 triangles. Let's go ahead and get started with right triangle trigonometry. Now, if you recall, the way that we defined trigonometric functions was using an angle in what we call standard position, and basically using a point on the terminal side of the angle and the distance between that point and the origin and the coordinates of that point. We were able to define all of those ratios, right? So what we would like to do is now free ourselves from having to be stuck in standard position and just look at any right triangle in this manner. Notice that when you're looking at a right triangle and an angle other than the right angle, remember that those two angles will always be acute, because their sum is 90 degrees, right? So neither one can be more than 90. So both of them are acute. So this is why we say trigonometric functions of acute angles. And notice that the way we're going to be defining the trigonometric functions, so that we don't need to worry about being in this standard position, is when we have an angle like alpha here, we know that one of the sides of that angle is going to be the hypotenuse. The other side we'll call the adjacent side. So the one that is not hypotenuse we'll call the adjacent. And then there's going to be a side that's going to be opposite that angle, which of course we'll call side opposite. Using that, then we can go ahead and define the trigonometric functions of alpha in this way. So we can say that the sine of alpha is opposite over hypotenuse. Okay, side opposite over hypotenuse. Now in this case, of course, it's still consistent with that. So even if it were in standard position, it would work the same way. So you'd get y over r. Notice that is opposite over hypotenuse. Cosine of alpha will be defined as the side adjacent over hypotenuse. Notice that even in standard position, it's consistent, because you get the adjacent side here to alpha is x and the hypotenuse is r. So same thing. Now tangent of alpha will be opposite over adjacent. Again, notice it works here too. Opposite y over x. That's exactly opposite over adjacent. Cosecant will of course just be the reciprocal of the sine, so r over y, or hypotenuse over side opposite. And the secant of alpha will be the reciprocal of the cosine, so it'll be r over x, or hypotenuse over adjacent, right? And cotangent will be the side adjacent to the side opposite. And of course, all of that will be consistent with our previous understanding as well. Now, one helpful mnemonic device is this phrase, this word right here, SOHCAHTOA. It's not a real word. It's just a shortcut to help us remember these relationships. So the sine is opposite over hypotenuse. Ka, so the cosine is adjacent over hypotenuse. Toa, so tangent is opposite over adjacent. So SOHCAHTOA is a very nice mnemonic to help us remember all those relationships. Okay, so here we have a right triangle, and we're going to find the sine, cosine, and tangent values for angles A and B. So for this angle and this angle. So the first thing we'll go ahead and do is we'll go ahead and find the length of this missing side, right? So let's go ahead and set up the Pythagorean equation for that particular triangle. And we know that now it's very common practice that if an angle is labeled capital A, we label the side opposite using lowercase a. So we'll stick with that convention. So we have a squared plus 8 squared equals 17 squared. Remember, let me go ahead and write the general equation first, just so that I'm consistent. I always recommend that L1 squared plus L2 squared equals h squared. So a squared plus 8 squared equals 17 squared. This is just leg 1 squared plus leg 2 squared equals hypotenuse squared. Legs are, of course, the two sides that form the right angle. So we get a squared plus 64 equals 17 squared, I believe is 289. Let's be sure. Okay. Now a squared is just going to be 289 minus 64. So we get 225. So a normally would be plus or minus the square root of 225, but because it's a positive length here, we just take the positive square root of 225, and that of course is 15. Okay, so now that we have that, we can write all the particular function values we're looking for. So sine of a, remember, you can always write SOHCAHTOA for yourself. I always, in fact, like to write it like this. Okay, because we know it's going to be a ratio of those two, like that. So this is the numerator, that's the denominator. So this is also a nice way to write that. So sine, as you know, is opposite over hypotenuse. So notice that for a, the opposite side is the a which we found. We know what it is now. It's 15. So it'll be 15 over the hypotenuse, which is 17. Cosine of a will be adjacent over hypotenuse. So notice for a, the side adjacent is has length 8 over hypotenuse, which is 17, and tangent of a is going to be opposite over adjacent, so 15 over 8. All right, so that's how we handle those. You should pause the video and go ahead and get the values for b, sine of b, cosine of b, and tangent of b, and then compare your answers to mine when you come back. So welcome back. Sine of b, sine is of course opposite over hypotenuse, but now we need the opposite of b, so that would be 8 over the hypotenuse, which is 17. Cosine of b will be adjacent over hypotenuse. Now the side adjacent to b is 15. Remember, every angle is going to have two sides, right? Well, one is the hypotenuse in a right triangle, so it's the other one that we consider to be called the side adjacent to that angle. So adjacent over hypotenuse, so 15 over 17. And the tangent is opposite over adjacent. So the tangent of b will be opposite, which is 8 over 15. All right. You may notice an interesting situation here where the sine of a is the same as the cosine of b, and the sine of b is the same as the cosine of a. That is not accidental. And that's precisely why we have the names sine and cosine. That's because these two functions are what we call cofunctions, which we'll get to very, very soon here. All right, so is this soon enough for you? Cofunctions. That's what we're going to talk about next. All right, so the first thing we note is the fact that the sum of the two acute angles. Remember, here's a right triangle, and the angle which is 90 degrees, that's of course a right angle. These other two angles, as we discussed, have to be acute because their sum is 90 degrees, so neither can be more than 90. Both of them are going to be between 0 degrees and 90 degrees, so they're both acute. More interestingly, notice that if you add them, they will have to add up to, their measures will have to add up to 90 degrees, because then you add them to this and you get 180, as we know from the triangle sum theorem. So we note that also here we show the standard notation. The side opposite angle A, we use the lower case a. For opposite angle B, we use lowercase b, and for C, we use lowercase c. So just for the sake of simplicity, let's say that the measure of angle A is just called A, the measure of angle B is just called B, and the measure of angle C is just called C, right? So this way we don't have to keep writing measure, angle, etc., right? So we know that A plus B plus C equals 180, right? So A plus B plus 90 equals 180 because C is a 90-degree angle. So we get A plus B is 180 minus 90, so we get A plus B equals 90. This is what we discussed in words. Now you can see it laid out here algebraically. So this tells you that angle A and angle B are complementary. Remember, when the sum of two angles is 90 degrees, we call them complements of one another, right? And of course, A is 90 minus B and B is 90 minus A. This is a mutual relationship. If one angle is a complement of another angle, then the other angle is also a complement of the first angle. So we also note that if the sine of A, here's A, sine is, remember, SOHCAHTOA, opposite over hypotenuse, so A over C, right? Cosine of A is B over C, and tangent of A is opposite over adjacent, A over B, right? Notice that for angle B, we end up with these relationships. Sine of B is opposite over hypotenuse, so B over C. Cosine of B is A over C, and tangent of B is B over A. Now, we notice that the reciprocal functions are all going to be just the reciprocal of those, right? Cosecant of A is C over A, secant of A is C over B, and cotangent of A is B over A. And the same with the reciprocal functions for B. Cosecant of B is just the reciprocal of that, C over B. Secant of B is the reciprocal of that, which is C over A. And the cotangent of B is the reciprocal of that, which is A over B. We further notice that the sine of A is the same as the cosine of B. And remember, B is 90 degrees minus A. So the sine of A is the same as the cosine of 90 minus A. And it is for this reason that sine and cosine are considered to be cofunctions. If the sine of an angle equals the cosine of the complement of that angle, that's what makes the two functions cofunctions. Notice that the cosine of A is the sine of B. Here is cosine of A, and there is the sine of B. Notice they're both B over C. And again, that means which is equal to the sine of, and remember, B is 90 minus A again, right? Etc. Notice the same kind of cofunction relationship exists between tangent and cotangent. Notice tangent of A is A over B, right? Now, what is cotangent of B? That's also a over b. So tangent and cotangent are also cofunctions, therefore the name, right? Tangent, cotangent. All right. The same exact thing also holds between secant and cosecant. Notice cosecant of a is c over a, and what is the secant of b? Also c over a. So secant and cosecant are also cofunctions. Now you understand why this relationship between the names exists, right? So make sure that you understand these relationships, pause on this page, get comfortable with all this, and we'll move forward after that. So now we're ready to go ahead and formally introduce the concept of cofunctions. By definition, two functions f and g are said to be cofunctions of one another if f of x equals g of 90 minus x. What does that mean? That means g of the complement of x. And g of x equals f of the complement of x as well. So note that we just established on the previous screen that sine of a is the cosine of 90 minus a. Cosine of a is the sine of 90 minus a. Tangent of a is the cotangent of 90 minus a. Cosecant of a is the secant of 90 minus a. Secant is the cosecant of 90 minus a. And cotangent of a is the tangent of 90 minus a. So we have established this relationship for these pairs. So we conclude that sine and cosine are indeed cofunctions. Tangent and cotangent are cofunctions. And secant and cosecant are also cofunctions. Even though the concept of cofunctions is a general one that can hold true for any function that satisfies it, they're almost exclusively used in trigonometry. All right, in this example, we're going to write each of these expressions using a cofunction. So we know that, for example, sine of 57 should be the same as the cosine of its complement, right? So sine of 57 degrees should be the same as the cosine of the complement of 57 degrees, which is 90 degrees minus 57 degrees. So we go ahead and compute 90 minus 57. We end up with 33, which is cosine of 33 degrees. Now you can actually verify this to satisfy yourself. Notice that the first thing you're going to want to do when you want to do trigonometric computations on a calculator is to make sure the calculator is in degree mode, because as we have hinted before, there is more than one way of measuring an angle. And now what we're going to do is we're going to go to the settings window. You have to find that on your calculator. And notice here, the default is radians. That's not at all unusual, because once you get to calculus and beyond, you're going to be dealing mostly with radian measures, because they're a very natural measurement for computations, and we utilize them very regularly in more advanced courses. So notice that what I'm going to do first is go with degrees. Of course, in a lot of building applications, degrees are still the measurement unit of choice. So it's not like we want to abandon degrees, it's just that we need to be comfortable with both, okay? So now notice that once you've done that, sometimes on most calculators you have to click somewhere else so that the change actually takes. Otherwise, the change might not become saved. So now I'm going to go ahead and exit here. And so let's try sine of 57. Notice we end up with this result. So if everything we've discussed is correct, the cosine of 33 should be the same value, right? So here's cosine of 33. Notice, identical. Okay? So that's not surprising. All right, now go ahead and see if you can do the rest of the problems yourself before you come back to the video. All right, so the tangent of 75 degrees we know is equal to the cotangent of the complement of 75, which is 90 degrees minus 75 degrees. So we get cotangent of, that should be 15 degrees. All right, if we want to verify this on a calculator to make sure we have done it correctly, we can take care of the first part in a pretty straightforward manner, right? After making sure we're in degree mode, of course, now that I've changed it, it's not going to go back to radians on its own. I'll have to go back and change it to radians if I want to. So it's safe, we can proceed, but always make sure that you have done the check initially. Now we just type in tangent of 75. Now, if you notice, there is something missing, right? There is no cotangent function on here. In fact, this is very common on most calculators. You see sine, cosine, and tangent. You will see the inverse sine, which here is referred to as arcsine, and inverse cosine and inverse tangent, but not the cofunctions. So you will have to handle those by understanding the concept of cofunctions. So remember that the cotangent, in other words, I cannot directly compute the cotangent of 15 degrees, but I know that the cotangent of 15 degrees is 1 over the tangent of 15 degrees. Remember, the cotangent of theta equals 1 over tangent of theta for all theta, right, where it's well defined. So instead of calculating the cotangent directly, I will just go 1 divided by tangent of 15, understanding that I'm actually calculating the cotangent of 15 degrees. So if I hit enter, I should get this number if I've done this correctly, right? Notice, in fact, we do. So the checks was just to, show you that this works. Now we'll go ahead and just do them without checking, right? We can be comfortable that we're doing this correctly. So secant of 36 degrees, of course, should be the same as the cosecant of the complement of 36 degrees, which is 90 degrees minus 36 degrees, right? So 90 minus 36, so 54, so we get equals cosecant of 54 degrees. And that's the answer you will leave. Of course, these are the expressions that are being asked for. Okay, so cosine of 45 degrees. Now I know that that should be the same as the sine of 90 minus 45, right? But notice that's actually going to be 45 as well. Now that's not accidental. That will become very clear for you very soon why that happens to be the case. So cosine of 45 and sine of 45 are equal. So here we're going to test our understanding of cofunctions by trying to find the value of x that will make this true, right? Assume that all angles involved are acute angles. So now we know that the cosine of an angle is the same as the sine of 90 degrees minus that angle, right? So this means that given that cosine of 3x plus 2 is the same as sine of x plus 4, that means 3x plus 2 must be the same as 90 minus that, correct? So like so, okay? Another way of thinking about it is, remember, you have, like, for example, cosine of 30 degrees should be the same as the sine of 90 minus 30, right? Which is what? 60, right? So one other way of doing this is to make sure that this and this add up to what? To 90. So 30 plus 60 equals 90. So more natural than writing this, right, which is going to be an equivalent, is to actually start out with this. The fact that 3x plus 2 plus x plus 4 should be 90. Notice that algebraically these are equivalent, right? So I'm just moving this expression to the other side and it becomes what? Positive, right? So this may be an easier place to start with. They're both correct. This is more natural. So in other words, these two, if this is the case, then these two should be complements, right? So we get 4x plus 6 equals 90. So 4x equals 84. And we end up with x equals 21. All right, so we were solving for x, and that's basically all we have to do. So make sure that you understand that and that you can handle that on your own before we proceed. All right, so you should be able to do this by yourself. Definitely pause the video, try to solve it on your own, and then come back. All right, so notice that here cotangent and tangent are cofunctions. So that means if the cotangent of one angle equals the tangent of another angle, then those two angles should be complements, right? Which means they should add up to what? To 90, exactly. So here we have 2 beta minus 18. Remember, we'll leave out the degrees just during our computation. And plus beta plus 18 degrees should equal to 90. Actually, let me be consistent, get rid of that degree for now. All right, so we get 2 beta and beta add up to 3 beta. Notice that the negative 18 and 18 cancel out, so we get 3 beta equals 90, so beta equals 30. All right, so for the final answer, however, let's go ahead and include the degrees so that we're consistent. In fact, we should take care of that in the previous one as well. So we did the same thing here. So for our final answer, we will include the degrees for consistency. All right, so that should take care of that. Next, we want to take a look at how the trig function values change as an acute angle. Theta, for example, here changes in size, right? And it actually becomes larger. So notice here we have theta, and this is a scenario where you can see the x value and the y value and the r value, right? Notice what happens if we keep r fixed, right? You don't change the value of r. In other words, this length stays the same. And we start just dragging this up so that the angle becomes larger, right? So notice in these two figures, the r remains the same. But watch what happens. The x is actually going to become smaller, right? And the y value is going to become larger, right? Notice this is continuously happening, right? X becomes smaller as you make the angle theta larger, and the y will become larger, right? And r, of course, remains the same. So as the value of theta increases, what happens to the sine of the angle theta, which is y over r, right? Notice because the y value is increasing and the r is not changing, the actual fraction is going to increase, right? And what about the reciprocal of y over r, which is cosecant? Notice the exact opposite is going to have to happen to cosecant, right? Because now you are making the denominator of a fraction larger but keeping the numerator fixed. So what happens? The fraction value is going to go down. Let's see if we can look at that in a more in the form of an example to see, make sure that makes complete sense to you. Okay, let's look at a fraction like 5 over 2. Remember, we were looking at r over y, right? So imagine that we keep the 5 fixed, right? That's the r, right? Now let's go ahead and increase the y value. So like 5 over 3. What happened to the overall value of the fraction? Well, this was 2.5, right? This is like 1 2/3. So what's happening? The value is actually going down. When you keep the numerator of a fraction fixed but increase the denominator, the overall value of the fraction goes down, right? So let's go one more, like 5/4. You see what's happening? That's even smaller than 5/3. 5/5, that's again smaller than 5/4. That's of course just 1. This is 1 1/4. So this is what I'm referring to. When the denominator of a fraction increases while the numerator is fixed, the actual overall size of the fraction decreases. On the other hand, if you look at, for example, 2 over 5, and this time we're looking at the sign, which is y over r, right? Now this time keep the 5, which is the r, in the denominator. So this was for cosecant. Now we're looking at the sine, right? Now let's say we start with 2/5, right? Now we're going to keep r fixed, but we're going to increase y, right? So for example, 3/5. Okay, what happened? What's the relationship between 2/5 and 3/5? 3/5 is of course larger than 2/5. So when you fix the denominator of a fraction but keep increasing the numerator, the overall size of the fraction actually increases, right? For example, 4/5, right? Etc. Again, 4/5 is larger than 3/5. So this is what we were referring to in the other screen, which we'll go back to now. So as theta increases in size, remember, all the while r is fixed, then the sine, which is y over r, increases, and the cosecant, which is r over y, decreases. Okay, that's what we're talking about here. Sine increases, cosecant decreases. As theta values increase, then of course this is all between 0 and 90 degrees, right? You have to limit yourself to acute angles, otherwise then things can change. So we're only concerned with theta values greater than 0 but less than 90, where all this that we're describing here holds true. Now what happens to x over r? Remember, x is decreasing. It's going from a larger size to smaller to smaller. So x over r is also going to decrease because r is fixed, right? And r over x, in fact, is going to increase. So the cosine values are going to decrease, but the secant values are going to increase. And the tangent values, which are y over x, right, are going to increase. Why? Because remember, the numerator is increasing, whereas the denominator is decreasing. And that's going to result in a larger fraction. Let's take a look at that. All right, so let's say we start with 3 over 5, right? Now we're going to increase the top, right? Remember, this is y over x. We're going to increase the y. We're going to decrease the x. So what happened when we did that? Notice this became larger. 4 over 4 is 1, which is larger than 3/5. Again, let's go ahead and increase the y, which is the top, and decrease the denominator, which is 4. Again, notice what happened. So when you increase a denominator and simultaneously decrease the denominator, you're going to result in larger and larger overall sizes for the fraction, right? So this is what we're talking about when we say that. So as theta values increase, the tangent values, which is y over x, increases, and the opposite is going to happen to cotangent. All you need to really remember is these three, because remember, those three are going to be the exact opposite of this behavior. So just remember that sine values increase. As the theta values increase, sine values increase, cosine values decrease, and tangent values increase. So sine and tangent increase where cosine decreases. And for those, just remember, just whatever these are doing, do the opposite to understand what those are doing. So let's test our understanding of what we just learned. So we want to determine if each of the following is true or false without using a calculator, right? So clearly justify your choice. So here we notice that 25 degrees is larger than 15 degrees. In other words, the sine, the angle is increasing from 15 to 25, right? So what should happen to the sine of the angle? Remember, as the angle increases, the y value increases, so the sine increases. So does it make sense that the sine of 25 degrees should be greater than the sine of 15 degrees? Absolutely, right? This definitely is true, because we have 15 degrees like this, and then we have 25 degrees slightly larger, right? Maybe too much, that's too much. Let's see. These are not, of course, exact, but just larger, right? So notice this part, the y part, is going to get higher, so y over r, which is remaining fixed, is going to be larger. So this is definitely true. Okay? How about cotangent of 25 as opposed to cotangent of 15? Now we know that 25 degrees is greater than 15 degrees, right? Now, if you recall, as theta increases from, between 0 and 90, then sine theta and tangent theta increase, but cosine theta decreases. Now, since tan theta is increasing, this implies that cotangent of theta should be decreasing, right? So if the angle is moving from 15 degrees to 25 degrees, right, we expect the cotangent of the larger angle 25 degrees to be less than the cotangent of the smaller angle 15 degrees. So therefore, this statement is false. So that's the kind of reasoning that you want to do in a problem like this. All right, next we want to study two very important special right triangles. The first one we'll look at is the 30, 60, 90 triangle. Basically, we know from geometry that if we bisect an equilateral triangle such as this, remember initially this is a equilateral triangle with side 2, 2, 2, angles 60, 60, 60, right? Notice that what happens when you bisect such a equilateral triangle, you're going to get two congruent angles here, so that means each will measure 30 degrees, right? And you will also bisect this side, so each of these pieces will have length 1, right? Now notice that if you take one of these, like say the one on the right, and just look at it in isolation, right? So you're going to have 1 here, 2 there, right? We don't know what this side is yet, so we can find it, right? So we can call it H, because that's what it's called here, because that's the height of the original triangle, right? Equilateral triangle. So we get h squared plus 1 squared equals 2 squared. That's just a, remember, this right here is the same as h. So this is why this is the Pythagorean equation, right? So we get h squared plus 1 squared equals 2 squared. So h squared plus 1 equals 4. So h squared equals 3, and h is going to be the square root of 3. So anytime you see a 30, 60, 90 triangle, remember that it's going to be similar to this triangle. Why? Because anytime two triangles have the same interior angle measures, they're similar, right? So any two 30, 60, 90 triangles are going to be similar. So this is what we will consider our reference 30, 60, 90 triangle. So remember, the side, if the side opposite the 30 is 1, the side opposite the 60 is going to be square root of 3, and the side opposite the 90-degree angle will be 2. This is going to help us solve any 30, 60, 90 triangle using the concept of similarity. So remember, we consider this to be our reference 30, 60, 90 triangle. All right, so now look at the trigonometric functions of 30 degrees. Here's 30 degrees, right? So we can consider finding those by looking at this reference 30, 60, 90 triangle. And we get the sine is, remember, SOHCAHTOA, right? So sine is, so we can always write that down to help us remember. SOHCAHTOA, right? So sine is going to be opposite, which is 1, over hypotenuse, which is 2. So that's where the 1/2 comes from. Cosine is going to be adjacent over hypotenuse, so square root of 3 over 2. Tangent is going to be opposite over adjacent, so 1 over square root of 3. Now, you should be familiar with both that as well as the rationalized form. Remember, if you take, let me show you over here. If you take 1 over square root of 3 and rationalize it, you're going to multiply, I didn't mean to do that, you're going to multiply top and bottom by square root of 3, and you're going to end up with square root of 3 over 3. So you should be as familiar with this form as you are with that form, and you should recognize both of those as the tangent of 30. Now, much more important than remembering what the tangent is, of course, is remembering what the sine and cosine are. Why is that? Because if you know those, you can get the tangent, remember? So let's actually, in fact, if you have those two, you can get all 6 values, right? So let's just take a look at the notion of why that would be enough to get the tangent. So sine is 1/2, cosine is square root of 3 over 2. So sine of 30 degrees is 1/2, and cosine of 30 degrees is square root of 3 over 2. So note, even without a graph, I can find the tangent of 30 just from those two facts, because I know the tangent is going to be the sine of 30 over the cosine of 30, right? So it's going to be 1/2 over square root of 3 over 2. And remember, we can do the outer product over the inner product. So it's going to be 2 over 2 radical 3. Those cancel out, and we get what? 1 over radical 3. As we discovered on the other page right here. Okay, so now the cosecant of 30, of course, is just going to be the reciprocal of that. So 2 over 1, which is 2, or you can think of it as hypotenuse over opposite, right? So you would just want to be reversing that direction, right? For the cosecant, hypotenuse over opposite will be 2 over 1, which is 2. secant of 30 you can get by just reciprocating that, which gives us 2 over radical 3, or you can just do adjacent or hypotenuse over adjacent, right? So 2 over radical 3. And if you rationalize that by multiplying top and bottom by square root of 3, you get this form. The cotangent of 30 will be square root of 3 over 1, which is just a reciprocal of that, which is just square root of 3. Now you can do the same for 60, right? So remember, you can find all those ratios for 60. Make sure that you remain on this page, become fully familiar with these, and get comfortable with them before moving forward. So here we're given a triangle. It's not in any particular standard position, and we're asked to solve for x and y in this figure, right? So first thing we notice that is that this is 90 and this is 60. This must be what? It can only be 30, right? So we can add that in. And then what's really useful is for you to draw another triangle. It would be useful if you draw it in the same kind of positioning, but this time let this be your standard 30, 60, 90. Remember, for the standard 30, 60, 90 triangle, if the side opposite 30 is 1, then the one opposite 60 is square root of 3, and the one opposite 90 is 2. So we get a 1 opposite the 30, we get a square root of 3 opposite the 60, and we get a 2 opposite the 90. So now you can see we have drawn our reference 30, 60, 90 triangle in a manner that is very similar to the one that we're looking at here. And now we can quickly set up ratios to solve for the unknowns. So we know that, for example, x is to 1 as 7 is to 2. And that's going to be as y is to square root of 3. Right? So just make sure that all three of these are represented on the top, right? And that these three are represented on the bottom. Now, of course, in corresponding positions. So now I'm going to take that equation and solve for x. So notice I get, by cross multiplying, I get 2x equals 7. So x equals 7 halves. And I'm going to take this equation and I'm going to solve for y. So 7 over 2 equals y over square root of 3. So we cross multiply, we get 2y equals 7 radical 3. So y equals 7 radical 3 over 2. So now we have solved for both x and y. Now, it's the easiest way to approach these, really, because all you have to remember is your reference triangle, and you can solve any 30, 60, 90 as long as you know the values for your reference 30, 60, 90 triangle, as like this. All right? The next type of special triangle that we want to look at is known as the 45, 45, 90 triangle. So to get the 45, 45, 90 triangle, what we do is we look at an isosceles right triangle, any isosceles right triangle, because if these two sides are equal, that's going to make the angles opposite them equal. And since those two angles are going to add up to, together with the 90 are going to add up to 180, that's going to force 2 theta to be 90, and therefore theta is going to be 45 degrees, right? So I was a little bit inconsistent here with my use of degrees. So if we're going to use them, let's use them everywhere. All right, so we know that each of these two angles is going to be 45. And also using the Pythagorean theorem, I know x squared plus x squared equals y squared, right? So I get y squared equals 2x squared, so y equals square root of 2 times x. We took the positive version because it's a length, and notice that the skipped step is that y equals the square root of 2x squared, which we of course can break up as the square root of 2 times the square root of x squared, and when x is positive, the square root of x squared is just x. You have to be careful. If you don't know the value of x, you should put absolute value of x. But when we know it's positive, because it's the length of a side of a triangle, it's safe to say that the square root of x squared is just x. So the interesting relationship between 45, 45, 90 triangles is that whatever the length of the two legs is, the length of the hypotenuse is always going to be square root of 2 times that length. That actually is sufficient information to use for 45, 45, 90 triangles. But I personally prefer coming up with a reference 45, 45, 90, which we can use to solve all other 45, 45, 90 triangles. And for that, we'll go to another screen. So remember that we said that the relationship between the legs of a 45, 45, 90 and the hypotenuse is that whatever the length of the leg is, the hypotenuse will be square root of 2 times that length. Now, of particular interest to us will be an isosceles right triangle with legs of length 1, because then this hypotenuse is just going to be square root of 2 times 1, which is just square root of 2. So 1 square root of 2 will be the measurements for the reference 45, 45, 90 triangle. So for a 45, 45, 90 triangle, we remember that if the sides opposite the two 45-degree angles are 1, then the side opposite the 90-degree angle will be square root of 2. This will help us solve any 45, 45, 90 triangle using the concept of similarity. Let's take a look at this problem. We're supposed to solve this triangle, and all they give us is the fact that these tick marks indicate that this is indeed an isosceles triangle. Remember, because it's isosceles, that means alpha and beta should both be what? 45 degrees. So this is a 45 90 triangle in deep disguise, right? Notice that because the alpha and beta are both 45, that's going to, and these two sides are equal, that's going to make x equal to 1. And remember, this is exactly the reference 45, 45, 90 triangle, right? In fact, in deep disguise. So we know that y is going to be what? Y is going to be the square root of 2. So here's a language that we haven't really discussed: solve the following triangle. So what does it actually mean to solve a triangle? Well, to solve a triangle simply means to find the lengths of all three sides and the measures of all three angles. Remember, a triangle has 1, 2, 3 sides, 1, 2, 3 angles, right? If you find the measure of all of those, then you have solved the triangle. So for this one, we know that alpha equals 45 degrees, beta equals 45 degrees, and this has a 90-degree mark next to it. We don't really need to worry about it. We know that's 90 degrees. X is 1, and y is the square root of 2. Okay? All right, so here is another triangle we're supposed to solve. Definitely try to solve it on your own before you come back. This will be our last example, so give it your best shot. All right, so now that you're back, in order to solve this, what we're going to do is we're going to draw a reference 45, 45, 90, realizing it is in fact the 45, 45, 90. If this is 90 and that's 45, this can only be what? This can only be a 45. So we're going to draw the reference 45, 45, 90 in a manner that looks very similar to this. So we'll set it up like this, right? Let me try that one more time. Slightly better. All right, so for the reference 45, 45, 90 triangle, we know that if this is 1, that's 1, this is going to be square root of 2. Remember, 45, 45, 90, the 1, 1 square root of 2 is what goes below, right? For the 30, 60, 90, you want to remember 1 square root of 3, 2 to help you remember the reference triangle. All right, now we can set up the proper proportions in order to solve for x and y, right? So notice that, by the way, do we need to solve for both? As you know, x and y are equal, so we just need to worry about solving for 1, right? So x is to 1 as, I definitely want to get 7 involved because that's a value that I know. So 7 is the one opposite 90, so 7 is to square root of 2. So x is to 1 as 7 is to square root of 2. Now I just need to solve that for x. So if we cross multiply, we get square root of 2 times x equals 7. So we get x equals 7 over square root of 2. If we rationalize by multiplying top and bottom by square root of 2, which we should always do, we always want to give our answers in rationalized format. So we end up with 7 square root of 2 over 2. So remember, x is going to be 7 square root of 2 over 2, and y is also going to be the same as x. So that's, we don't need, we could go through the same procedure, but we really don't need to because we know those are going to be the same. All right, so that's how you utilize the reference 30, 60, 90 and 45, 45, 90 triangles to solve any 30, 60, 90 or any 45, 45, 90 triangle. All right, so that should do it for this lesson. Please make sure to do your assignments on time and stay safe till we meet again for the next lesson.